We're going to continue our study of oscillations with damping and resonance in this video. The first point to make is that we've been looking at simple harmonic motion, and that motion has continued on, ideally, with our trig functions, okay, without the amplitude decreasing. And without damping, right, our oscillations end up looking something like this. This perfect example where they continue to oscillate without any decrease in amplitude, all right, which we know not to be the case. So I should draw it like this. All right, and the fact is that the amplitude is going to decrease. Okay, and the reason for that decreasing, right, is damping. And the idea of damping is that there's a force that's going to be acting on the system in the opposite direction to the direction of motion. So this force, all right, that acts this way, is damping is due to a dissipative force, you could call it. All right, and this force, okay, is non-conservative. It's a friction force. All right. What that means is that when we talk about transfer of energy, you cannot recover that energy. That energy is lost. All right. So, an example of a dissipative force, would be friction. All right, friction within the spring itself. Okay. Is what can cause damping, the amplitude to decrease. And we can also use an actual damper. We can put a damper in place in parallel with that spring and slow down the vibrations of our object. All right. So the effect, all right, of this is that the system loses energy as this is happening, and the amplitude also decreases. Remember, energy is directly proportional to the amplitude squared. So what you end up with is a curve that looks something like this. All right? The amplitude or displacement versus time function, the amplitude ends up decreasing over time. There are various levels of damping that can occur. If we look at a quick example, mass on a spring, okay? If I vibrate this mass, I turn the friction up. You can go to FET, all right, that website, fet.colorado.edu, it's up here. And if I bounce this mass, I have the friction turned on such that the mass will eventually come to a rest. I can give it lots of friction, and what ends up happening then, after I let it go, is that it takes less time, all right, to get back there. These are all situations that we would consider underdamped. And the reason that it's underdamped is that there's still an oscillation. It still goes back and forth, all right, but eventually does come to rest and the amplitude ends up being 0. So we have a graph of position versus time, and when we look at that graph, this would be an example of a lightly damped or underdamped situation. Okay? And an example where you want this would be like car shock absorbers. You want the car to absorb some of the shock, therefore, you know, to decrease the amplitude of the vibration, but you don't want the car, okay, to not vibrate. In other words, you don't want the wheel to not vibrate a little bit. That balance is actually good. It actually prevents the car from bottoming out when you do hit a bump, okay? If it was damped anymore, all right, the wheels would get stuck every time they would get pushed up for a little while, okay? So you need to have a little bit of a vibration, but for that vibration to die out very quickly, all right? So that's this considered situation that we consider lightly or underdamped. Critical damping is when you have, this is light or underdamped, the minimum amount of time to stop the oscillation. All right, so that's, all right, the ideal situation where you only have one oscillation. In other words, you go from the amplitude straight to 0 in the minimum amount of time. All right. The next example, all right, I put these graphs next to each other. This was the critical damping from the previous slide. All right. This one's called overdamping, or sometimes, I guess in IB, they call it heavy damping. All right. And this is a situation where it takes a long time for the object to come back to the equilibrium position. All right. This is what happens if you were to drop an object into a viscous fluid, for example. All right. The above object, oftentimes at school, all right, if you see the doors, they have these little arms connected to them, and you notice that the arm, all right, moves back at a constant, relatively constant velocity, actually, all right, and they're typically critically damped. Any doors that have those little arms on them, they're meant to keep the door from slamming shut, but to move back at a speed where it'll stop moving once it hits the door jamb. So if the door jamb wasn't there, it would be kind of like an oscillation. So that's how that behaves, all right? Okay, so the next thing we're going to talk about here is resonance. An object, okay, any object that is displaced from equilibrium, all right? So if we go back to our example with the springs here, there we go, our masses and springs, turn the friction off. Based on the amount of mass and the stiffness of the spring, this guy's going to vibrate up and down at a given frequency. And remember, we calculated that frequency, okay? That frequency, we talked about this before, the natural frequency an object will vibrate at, if we look at it in terms of the angular frequency, if there's no damping, right, we just consider it to be this. Well, if not, all right. What we can do is we can force an oscillation, all right, if the oscillation matches this frequency, all right. When this is happening, this is something that we call resonance. So in other words, let's talk about some examples of resonance. Resonance happens, say, when there's an earthquake, and if a building is built a certain way, all right, and it matches the natural frequency of the building matches the frequency of the earthquake, that building will vibrate. Same thing happens with musical instruments, all sorts of examples of resonance. So we have vibrations in machinery, okay? When you're driving your car, sometimes if you're driving it down the highway, some people's cars, once they get up to a certain speed, start to vibrate. And that's because the engine itself is vibrating, and if that vibration matches the natural frequency, the natural resonant frequency of the car, the entire car itself will start to vibrate. Mechanical engineers design systems that help to absorb that vibration and help to make sure that the car itself is stiff enough that it won't vibrate. But poorly designed cars or old cars, this is going to happen. So there's many examples of resonance, many good and bad examples. You have them all right there. I want you to read them because they are all examples we will be using for the rest of the year. We'll be talking about musical instruments coming up soon. We'll be talking about the greenhouse effect. All right, microwaves use resonance. All right, the microwaves that are being sent into the space inside of the microwave oven, if you will, end up having the same frequency as the resonance frequency of water. So it causes the water molecules to vibrate. When the water molecules vibrate, okay, you end up with a situation where they're heating up. Okay, any extra motion means that they're heating up, and that heats the food up. So that's why actually food ends up being dry in the microwave, right? Because you're boiling off all that water, purposely, moving the water to heat the food up. So let's talk about this really quickly, okay? There are different things that are going to affect how a object will vibrate or not. One of the big things is the frequency of the driving force. If we apply different frequencies, right, to an object, and we'll say this is the natural frequency of that object, what we'll see is a response curve, an amplitude of that object's vibration is going to just peak right around the natural frequency, okay? So basically, whenever you apply driving force to a system, all right, its response is that there will be a forced oscillation. There are different factors that will affect the sharpness of this curve. You see right here that one of the factors is the amount of damping. You see 3 different frequency response curves, all for different amounts of damping. Okay, light damping is going to give us a much sharper, all right, frequency response curve. Heavy damping is going to give us that much lower frequency response curve, okay? So the things that affect the sharpness of the curve are the frequency, that's what's on the x-axis of the driving force. Of course, the natural frequency of the system, all right? Right there is that F naught, we'll call it. So the natural frequency. The amplitude of the driving force. And finally, for 4, the amount of damping. All right, these are the 4 different things that you're going to find. We're going to do a simulation in class on Monday. That's it for the notes, okay? And hope you have a good weekend.